if I understand, you have speaking about the supercapacitors. Just I want to know what are or what is the main limitation of this method. Just this. Thank you.
Of the recycled polymers? No, there is no limitation, absolutely nothing that actually prevents you from making highly performant supercapacitor electrode materials. No, there's no problem at all with that. It's just what's limiting when you make the supercapacitors is often it's the surface area, it's the conductivity. It means if you start with a polymer, you cannot use all polymers. You cannot all recycle polymers. For instance, if you take like just pure organic polymers, I think it will be difficult to transform them to the graphene type material. So like if you take pure fluoropolymers, it will be difficult to make an electron materials. But otherwise, yes, if you have, I would say, polymers with double bonds or aromatic bonds groups, then there's no problem to make something which is conducting. Because the important thing is CO2 laser, just to provide a lot of energy, then you burn your polymer. So you generate CO2, unfortunately, that's, I would say, the most limiting aspect, you generate CO2. But then also you generate aromatic bonds, which is a graphene type material. So any polymer that could actually potentially drive you to the graphene type material, there's no problem, you can use it, there's no limitation. But as I said, I think we tried on some different polymers. I think we had a European project on recycling photovoltaic panels, and there's a lot of polymers used as well. So at some point I wanted to try this polymer if we can make graphene type and supercapacitors. And it turns very difficult actually with the CO2, just using the laser, it's quite limiting. So it depends on the structure of the polymers, definitely. That's the main limitation.
Any other question, please? Yes.
Thank you very much for your presentation. And my question is, you use the laser processing technique to upcycling or recovering the polymer waste. Is it possible to use the same method to upcycling the materials composites? Thank you.
Well, I focus just on polymers. Yes, on the polymer side, there's no problem. Using this technique of laser writing, commonly I would say probably 90% of the polymers can be easily. Whether it's a waste or it's not a waste, there's no problem. So if you look on the literature, there are even people taking orange peels, or the waste from potato, and you can write directly on that. It's a starch, so you can write directly and make graphene out of it. So in terms of whether it's a processed polymer or it's not a processed material, there's no limitation for that. It's a laser writing. Any type of material which is based on carbon, it will be transformed on graphite type or graphene type. So there's no limitation for that, unless, as I said previously, probably if you have some hydrocarbon type, like polyethylene, or this probably, I'm not sure if it will be working as good as not. Otherwise, yeah, it's a laser writing. You provide energy, which is much higher than the carbon-carbon bonds. So you break the bonds, and you transform that. Also, you remove the hydrogen, and you generate aromatics. So you can do almost, I wouldn't say in any, but most of the materials you can do that, if they're carbon-based. Any other questions? Yes, please.
Thank you, Professor Mukharroub, for your talk about upcycling waste plastics. I just want to know what is the role of amexine in your investigation, and also MOF, because the MOF are material who have high absorbance. What is the role in your investigation? Thank you very much.
Thank you. Yeah, thank you. Yeah, good. Maxine is a 2D material, so it's a family of 2D materials. So it's also used for as an electron material. So it's like graphene, Maxine. You have tons of 2D materials. It has good conductivity, high surface area, so that's potential also. We used it for electrode material for the supercapacitor. So there's nothing different from, well, of course there are properties which are different, but it's just a material. It could be any other material. As soon as you have, actually, it allows you to have a stable under operating conditions. It's not corroded, because the big problem when you make supercapacitors, if you have the electrode, you put an electrolyte. If the material is not stable, it will corrode, it will decompose, then of course the supercapacitor is not stable. So MXene is a type of material which has a high surface area, good conductivity, but also because it's a combination of a transition metal and it's a nitride, like it's a carbonitride. So there, you can make, I think there are like 2,000 different MXenes. There's nothing more than just a 2D material with good properties. Conductivity, high surface area, and stability, chemical stability. Okay. The MOFs, we didn't use the MOF directly, but MOFs, as I said, well, if there is a Nobel Prize for MOFs, it means there is a lot of applications you can, because it's very nice structured material, so it's a porous, so you can play with the ligands to actually have really controlled for size. So we can use it as a membrane, selective separation. You can use it for storage because it's a porous material as well. People make selective reactions because there are only few molecules if you select the appropriate size. And also biomedical application, catalysis, because it does actually have a transition metal, so we can use it in catalysis or electrocatalysis. So the application for MOFs are just, there are probably thousands of reviews on that, and people tried everything. And it's easy. The only big problem for MOF, especially when it started years ago, I think like 2002, I think, if I'm not mistaken, the first MOF was reported. It's the stability in water. Because you take an organic, it's coordination chemistry, there's nothing else. You take a monomer, you add a metal, then they assemble. It's a self-assembly process. But most of them actually are not soluble or stable in water. So whatever you deal with something which has water in it, then they're not really useful. But people worked with the chemistry, and now, of course, you can make really very stable MOFs, and people use them, yes, for plenty of application. Whether there is industrial application of MOF, it's another thing. Today, probably not. But at the lab scale, up to proof of concept, yeah, there are so many applications of this. You're welcome.
Maybe I will finish with the last question, Professor.
Yes,
Rabah
yes.
Mokhroubi, have just one
Yes.
question.
Yes.
Yeah, my question is a general question. I mean, you talk about plastics waste, but we know that generally these plastics waste are contaminated. So in this case, what would be your approach? How you can deal these plastics waste with all these applications? I understand that with PET, for instance, which is a normal polymer, not contaminated, this is possible. But in general, all the plastics waste is subjected already.
Yeah, I fully agree, and it's a very good point and comment indeed. This is not the only problem. Of course, when we give a topic to a student, you don't put him on a... There are a lot of polymers as well. It's a mixture of polymers. If you take the... I think so far for packaging, it's not one polymer. And the chemistry apply, of course, then it's not anymore. We took the PET because it's the simplest. Indeed, it's clean. You take the bottle of water, you cut it, and then you hydrolyze it, it's no problem. But if you go to other polymers, first, the depolymerization would not work the same. That's the first one big issue and problem probably. But the issue related to the contamination, definitely yes. Either you clean, or now what people use most of, even at the industrial level, you take what you call a solar concentrator, so we generate quite huge amount of energy, then you melt the polymer. Then probably, yeah, then one hopes that you can separate the chemicals from the contaminants, or you have first to clean the waste to make it at least clean enough, then you can go for the second treatment. Yeah, that's, even the plastic, this plastic, if you take it outside, it's full of sand, it's full of soil, it's full of anything, yes. That's a big, big issue. So yes, no matter what you do, yes, if it's meant for chemistry, it has to be clean. And that's, again, will generate additional waste.
Okay, thank you very much. Let's applaud again our speaker.